Hello everyone, welcome to the day 6 in the 30 days LLM mastery course. In day 5, we saw about the different positional encoding methods and its impact on attention. There, we would have used a simple attention mechanism known as multi-head attention mechanism, but there are different types of attention mechanism, and in this video today we are going to see about the different attention mechanisms that exist, and similar to the previous video we'll see the mathematical formulation. And this video is going to be easier because positional encoding is more mathematical and attention is more architectural, the types, so it will be more easier to understand the representations. So there are different types: multi-head, multi-query, grouped query, a sliding window, disentangled attention. Every types will be explained as like in the previous video: pros, cons, why you should use it, how it works, and then finally the code with all the visualization. Everything will be done. So stay till the end and have a fun journey ahead. Let's start with multi-head attention. The multi-head attention is a key component, and that is the novel component which was introduced in the paper Attention is All You Need, where it extends the idea of using the attention, which is scale dot product attention, to attend information from different representation subspaces at different positions. So what it means is that with attention, right, in multi-head, what we do is instead of focusing on one aspect, we split it as multiple heads and then focus on multiple aspect, right? That is what is said here. Okay, so here we'll use multiple heads to focus on multiple positions and multiple information relationships and all. So that is the core idea of multi-head attention. So what happens in the multi-head attention? Here I'm not going to speak about scale dot product, that remains the same everywhere, right? So here we'll be starting with the multi-head, which is concatenation. Okay, from there we are going to start in this. So here if you see, this image will provide you a lot of context actually. Okay, the multi-head attention is where each query will have a key and then a value, query key transpose into value. But if you see multi-query, this is multi-head and this is multi-query. Okay, multiple queries will have a single key and a value. Here a group of queries will have a key and a value, that is grouped query, and then this is multi-query. Okay, this will explain simply about the three types of attention already. Okay, in a definition kind of a manner, we'll see it later, but this is the difference between these three. Okay, there are other two types which we'll see later, but these are the main three types at top first. Okay, so the multi-head is finally an attention type where we'll have multiple heads and each head will have an attention focus, and all of those are concatenated together and will be multiplied with a WO, which is the projection, right? And in each attention you will be calculating query key transpose, and then it will be multiplied query query with the weight query, and then key with the weight key, and then value with the weight value. All will be provided as inputs, and then you will follow this normal attention function, which is softmax of qk transpose by root of dk into v. This is the conventional one, right? So why you can use this? It is parallel processing. Multiple attention heads can be computed simultaneously. So it can focus on different features. So it can capture diverse features. The representation is better because it works in different subspaces, and also the performance is better than single head attention. Always there is a saying, right? Group is better than a single. So that also applies here. So how this will work? First, you will project your QKV into H different subspaces. H different subspaces is number of heads. Okay, and then you will apply scale dot product on each. You will concatenate those output, and then a final linear projection will be combining all those information which you just stacked while you concatenate your output. Okay, that is what happens in multi-head attention. And as far as the pros is concerned, it is parallel processing, diverse feature capture, improved representation, enhanced performance. Also, it is very flexible. Okay, you can add any number of heads you want. So with number of tasks increase the number of heads, so that for task space also it will focus in different manner. With multi-head, the problems are it is highly complex compared to a single attention, and also some heads might learn similar patterns, which means those heads are redundant, right? Like, if I'm having 10 heads and 3 heads are say learning the same thing, which means only 7 heads are required here. 8, because 3 are same, 1 should be the unique one there. So 8 are the heads required there. So there is a potential for redundancy, and also understanding what each head learned will be kind of difficult, but not so difficult. Still, you can print the attention map of each head. That is also possible. But single head attention is very direct, but here you need to go one layer down and then find it. It is memory intensive, and the number of heads is going to be hyperparameter sensitive. As far as comparison with other methods is concerned, across other methods versus single head attention, this is going to be more better performance, better feature capturing and all, but with increased cost complexity. While you compare it with multi-query attention, multi-query attention will have the same key values across every head. So in multi-head attention, what we do is for each head we'll have a query and key and a value, but in multi-query attention, the query alone will be separate for each head, but key values are going to be the same. But in grouped query, we are going to separate it as group with some projections having shared. Sliding window, it is something very separate. Multi-head attention will focus on entire sequence, but sliding window will focus on local context. Okay, it will have a window of view, and in that window only it will be able to see. When you compare it with the descent angle attention, it is another method where descent angle multi-head attention uses single attention mechanism, but descent angle attention will use 2 attentions. One is content based, another one is position based. Okay, so these are the differences between multi-head and the other mechanisms. Now let's jump into multi-query. Like I said, these are very simple. Okay, the codes are going to be very simple. The attention mechanisms are going to be very simple. Actually, there is going to be a lot of repeating. Okay, if you see this differences itself right, you will be able to understand what will happen in behind. So let's go let's go deep. So multi-query attention, if you see, it's a variant of multi-head attention to reduce the computational and memory requirements. Because if we see here, the performance was good, but the memory intensive is an aspect which has been a problematic one. So what they did was they said, okay, I'm going to have different queries. Query, I'm not going to say what I want is more important, but key and value is going to say about what are the things available and what is the value of that, right? If I provide it even at different head, right, it doesn't make any sense, because the context always remains the same. What I want differs across time steps, right? So what they did was, okay, we'll separate query for each, but the key will be the same. So here you can see, right, the input for attention head will be, for example, attention head 1 will have query 1, something like that. Okay, but the key and value always remains the same for every attention head. Okay, so here, why should you use this? It will have reduced memory usage compared to multi-head attention. It will be faster to infer because you don't have multiple keys and values. But since you are reducing the keys and values, right, instead of having 8 keys and values, you're having only 1. It will be similar results, but there will be a performance degradation for sure. Comparable performance is what you will achieve. You will not achieve the same performance as multi-head, but that could be a good trade-off. That was a good trade-off when it came to the performance it was achieving. Okay, and the speed it gave, and then the reduced memory usage and all. So how does it work? First, what you'll do is you'll project the query alone through the different subspaces, and you'll project the key and value once to all the head. It will be shared across the head. You'll just expand. It's having the same stack repeated against for every heads. That is what is the second step. And then you will compute your dot product, concatenate it, and then apply a final linear of projection. That is common. Okay. So the pros are going to remain the same. Said, like, why we use reduced memory usage, faster inference, comparable performance, improved throughput, and also you need to work with fewer projection matrix, and also, like, fewer KV matrix, right? So it is going to be a simplified architecture than how it was before. But the cons is that it will limit the capacity of the model to some extent, like I said, and it is very less flexible because you have only one key value across every head. And also, interpretability will be challenging because KV is shared. So to understand, how much it impacted, that understanding is a bit harder. Okay. Other than that, multi-query is gonna remain the same. So if you are more performance oriented, you can try for multi-head. If you're more memory related performance oriented, you can go for multi-query. So as far as the comparison is concerned, the comparison is going to remain the same. Okay, multi-query, reduced memory usage, improves inference speed, but less in performance. Multi-query shares all key values, but here group query will have a group of keys and values for each heads, and that alone will be visible. Multi-query will have entire sequence context, but sliding window local context. Multi-query single attention mechanism, but disentangled content-based and position-based attention is there. Now, coming on to group query. You see, why group query came into the picture was multi-query and multi-head seemed like both extremes. Okay, one was focusing only on memory related performance and inference related performance, and the other one was more like, okay, I'll focus on accuracy, something like that. So there came a method known as GQA, training generalized multi-query transformer model. So what the method said was, I'll try to balance between the multi-query and multi-head. I'll try to get the efficiency of memory and speed of multi-query, and then I'll also not compromise on the performance. Still, there will be a performance compromise. Let's say if there is a accuracy drop of 3% with multi-query, it will be just 0.5% with group query. Okay, so what here it will happen is, instead of combining the heads, right, you'll combine the groups. Okay, so each group will have number of heads. So let's say you have 8 heads, right? What we'll do is we'll have 4 groups, which means 2 heads will be there for each group, and for those 2, the attention will be normal. So it is like adding a layer in between. Okay, instead of doing let's say if it is multi-head, right, it is like one group 8 heads. So if it is multi-query, multi-head is the way you can compare it better. With multi-head, it is just one group which has 8 heads, and all of those are concatenated together later. But with group query, it is like you're splitting that one group into 4 groups, which with each group having 2 queries and 2 keys and 2 values. Okay, so this 2 keys with same key and same value. Okay, 2 query with same key and same value. Sorry for the confusion. Here you can see the mathematical representation, right? For that group, the K and V will be same, which means if I have 4 groups, it will be 4 keys and 4 values in place of 8 keys and 8 values in case of multi-head attention, and 1 key and 1 value in case of multi-query attention. It is like bridging in between, right? So they have just added a middle layer kind of a thing with number of groups. Now, why should you use group query attention? It is balancing both. It is improving efficiency. It is also maintaining the expressiveness of multi-head. It is more flexible. You can add the number of groups or reduce the number of groups based on the tasks you have. And also, it is very much compatible with any multi-head attention pre-trained model. You can just convert it easily. And how this will work? First, divide the number of attention heads into groups. Like I said, if it is 8, let's say you want 2 key value per group. Okay, so it will be 4 groups. You will do query projection across each head in the group, and then for each query, it will have same key and value across the same group. Okay, for across groups, it will have different key values. Same group, same key, same value. Different group, different key, different value. but everywhere different query. Okay. Attention computation hereafter is going to be same. And what you'll do is you'll concatenate all the groups, which means you're concatenating all the outputs of all heads, and then final linear projection will be there. Here the pros and cons. Pros we already know, and cons are going to be like, the implementation is more complex because you are adding another layer, and also finding the optimal number of groups. Though it is flexible, it is harder to do. And also this has been a relatively new method compared to the other two, but nowadays people are using this a lot. But like other than this, there are not a lot of cons. So one could be said like, it is not always that you will achieve the best trade-off. It's not like you will find the 50% at efficiency and performance. So that is also there. Okay. As far as the comparison to other methods, I'm not even going to compare. You all know right now it is memory usage reduced, but also expressiveness is almost same to some extent. So it is like balancing between these two. Again, GQA have entire context length, and also it only has one focus of attention. This has two focus of attention, disentangled. Okay. So the three main handling types of attentions are done. Now there are two other types of attention for your clearance. These two are another type of like, it's a different way of attention. It is like different focus kind of attention, where these three can be implemented with sliding window. Okay. So sliding window can be a group query sliding window attention. Sliding window can be multi-query attention. Okay. Even sliding window could be a disentangled attention. Okay. So these all five are, interusable. That's why I said this is more architectural, like whenever you want, just plug and play whatever you want. Okay. So in sliding window, what happens is you'll have a window of context length you want to see. Let's say you have 1024. You won't see the 1024 tokens. Rather, you will see the tokens in your window. Okay. So this was released in a paper sometime before, but it became more famous with Mistral. Okay, this is the image from Mistral paper itself. So if I have a vanilla attention, right, it will see all the 5 tokens when it comes to the 5th token. But if my window is 3, it will just see the last 3 tokens, okay, from a given position. Now you might wonder, then I might lose the information, right? But if you remember, we have multiple layers in which each layer is coming up one above the other, right? We have multiple layers. Each layer would have focused already. So for example, if I'm seeing this layer, right, the first 4 tokens would have been seen, and that information would have been already there to the second layer before sending it to the second layer. So similarly, it will be additive, which means even the last head of the last layer will have the context from the first token, even the last token will have the context of first token. Now let's see in detail about sliding window attention. So what is sliding window attention? Sliding window attention is an attention mechanism that will restrict your attention computation to a local window around each token. Like I said, if it is this token, always, we are not going to see the forward side, right? With LLMs mainly being decoder, the forward side is always not going to be visible. We are going to see the backward side. And in the previous tokens, I'll be having the visibility only for the window of tokens I have. Now, why do this, why do we have this actually? Is there a problem in this? Yes, there are disadvantages, which we'll see later. But if you see, the most of the context, even let's say 1024, the first token is not going to impact the 1024th token. In odd cases, it might, but mostly, a context for a token will be there within let's say 200, 500 tokens, something like that. I'm not saying that small window will be used in training. Okay. While training, people usually keep around 2048 kind of window. Even 4096 is a very common window size nowadays, because they wanted to scale to 128K. Imagine I want to process 128K and I am computing attention for 128K tokens together. It will take a lot of computation and a lot more time. Okay. So that is why people use sliding window attention in combination with group query. Please remember that. Combination with group query is very important. Okay. Now, mathematically, how this works. Here, we'll be applying softmax on keys and values which are local. in the window. Okay, my context is the previous one, right? So those will be localized upon the window size. That goes without saying. Why should you use Windows sliding window? First, it is efficient. It will reduce time and memory complexity for long sequences. It will capture the local dependencies effectively. It is very scalable, and also it incorporates a locality bias. This is both an advantage and disadvantage. Okay, the tokens which are close to a token, okay, the token, let's say I, which is closer to a token J, will have more importance and effectiveness rather than a token which is, let's say, N, which is somewhere else. Okay, as far as the compatibility is considered, like, this can be easily combined with global attention. Okay, so there is a paper even, like, this will act as a local attention, and there will be a global attention where what they will do is they'll take the top 1024, let's say my global attention context length is 4096. Okay, they'll take the 4096 top tokens, and that will act as a context. There, like very less important words like redundant words like stop words, those all will be removed. But yeah, like, you can still combine with global attention easily. How this attention will work? First, you will define your window size. So first define a window size and then calculate attention within that window alone. Make sure that you apply the mask to prevent attention before and after the window. Aggregate information only from the tokens within the window. After you mask it, right, you will have zeros and ones. Wherever it is one, those information will alone be combined. And if you have a global attention, you will have another attention which is global, and that will allow certain tokens to be attended globally, and those will be combined together, added together. Okay, so the pros we all know. Cons, whatever we see as pro, right, there is a con in there. First, limited global context. It can't see long range. Like I said, yes, there will be a generalization. Like I said here, first token will be coming till the last, but still the same layer seeing all the tokens is more better. Okay, that will provide, like, some struggle to it. Fixed window size, how can I say, like, the last 100 tokens is the correct window. Optimal window size will differ for each sequence, and different parts of the sequence is also going to come into the picture, right? So fixed window size is another issue. There is a potential for information loss, and this is not suitable for every task. For example, if it is a summarization, right, it is better to have an attention over the whole context rather than a window, right? So task dependency is an issue, but it is an underrated issue. Okay, like, we won't consider this a lot. And then there is implementation complexity. It is more complex to implement efficiently. You can implement it easily, but it is more complex to implement efficiently with GPU acceleration. As we compare it with the other methods, all of those are going to focus on global context, while this is going to focus on local context. That's all. Okay. But there is another method which came, which is also a variant of sliding window, which came known as attention sink. Okay. There was a research which said that, like, if you have those previous tokens, right? So the good thing is the first token usually apparently contains the information of all the tokens a lot. Okay. In NLP itself, even with CV, if you compare, there's a token known as CLS token. The first token will have the information of every other token, and even to do a classification of image, that CLS token is more than enough. Okay. Here, just consider this token mostly has a context of all the token. Okay. What they will do is there will be a window. Okay. This is the sliding window which we see. Okay. This is window attention. This is sliding window. Okay. You'll move this window, and here you'll add the first token along with this window token. Okay. And this apparently provides the best result. Okay. Sliding window, if you see already, it is providing around 5.543. Okay. 5.43 is already a very good window. But if you see, when you go to attention thing, this is for very long context. If you want to go for very, very long context, right, at that time. Streaming LLM, which is the attention sync, has 5.40 perplexity. This is lower the better, and this has the better, the most best results you can say. Okay. Now coming on to the last type, which is disentangled attention. Okay. So if you remember, we'll always provide the positional embedding and the context embedding together. First, we'll add it, right? And then we'll provide it to the attention. That is how it works. But disentangled attention is a method where you will provide both of those separately. Okay. So here you can see you'll have query key values for context embedding and query and key for location. Okay. So this is a different method, and this has been used a lot in document related models. Okay. When you have document related models or models which you need to focus on localized information, they'll use disentangled attention because the position embedding information is retained. Okay. You're not just adding it, you're retaining it, you're computing an attention for the locations and saying like, at this location, there is a high possibility that I have my value. And that information is provided to the context as well when we add the context attention together. This is how it works. Okay. Now we'll see, when we go down, you will understand. And also when you go to the code, you will understand this even more better. First, disentangled attention is a mechanism where you will separate content-based and position-based components. And this approach is to improve the model's capability to capture both content and positional information independently. Rather than adding both of those together, if you keep it separately, the position information is retained. Okay. And also the context information. Both are unaffected, right? When you go to the attention. So that is the advantage when you go to disentangled attention. But like I said, if you have a disentangled attention with a window, it is going to become disentangled sliding window attention. And if you have a disentangled attention with the sliding window and a group query, it is going to become disentangled sliding window group query attention. Okay. All of these are mix and match. You can't mix and match the first three. Okay. The first three are separate types, but with that first three, these two can be add on. So mathematically how it works. First, it is going to be the same QK transpose by root of dk, but here you will also have an attention for relative position. Okay, there will be a relative position attention matrix, and then you'll once you do this, you'll as usual multiply it with value. Okay, the relative position attention matrix is calculated by alpha into r of I minus j, which is a learned relative position embedding, which is nothing but the nn embedding layer, which we saw previously. Okay, and then you'll add a beta as well. Now, why should you use this disentangled attention? First, it will provide better representation because both are separate. It enhances flexibility, and also the interpretability is better because if you add both of those together, you don't know what the model is focusing on. Now you can see how much the position is attended and how much is the context attended, how much it is impacting. And also the position bias is reduced because you're not adding together. Okay. Now, how this attention basically works, disentangled attention at around real time. First, you will compute the content-based attention, which is the standard scale.product attention. Then you will compute attention on the relative position embeddings. And then you'll combine those, you'll just add those. Not the combination is not something very new word and all, it's just addition. Okay. And normalization, it is to apply softmax on the probabilities you got from combination. And then you'll do multiplication with value, and then final attention is obtained. Okay. As far as the pros is concerned, it is going to remain the same, but also the learnable parameters, if you see, it will allow you to adjust the importance of content to position. Okay, if you want more learnable content parameters, you can have a more embeddings for contents and less embedding for position. But if you follow the same approach as before, right, you need to add those together, which means both of those should follow the same dimension. Okay, but here you can just add a final linear layer of projection from the attention, and then it would be easy to add. Okay, so you can easily adjust the parameters wherever you want to give more importance. And the cons is that first, it is more complex to implement since you're having additional computations for relative position embedding, like the attention computations. It is going to be extra computation, extra memory. The sequence length is going to become a very important thing because the relative position embedding which you use, it is going to impact the attention a lot. So the choice of sequence length is very important, and also it is a bit hard to train. Okay, and here if you see the comparison with other methods versus standard attention, which adds the positional information before itself, here you are having a potential to improve performance on tasks which require both content and position. That's why I said document related task. Okay, and if you compare it with other methods as well, like transformer excel, which uses relative position embedding, here you are attending the relative position embedding separately, so theoretically it is better. Okay, now let's see the programming part of this. Let's start with the most simplest method, which is multi-head attention. Okay, so right now we are seeing the multi-head attention, which is the most simplest form of all. How this works, let's walk through the code. As far as the initialization is concerned, first you will initialize the D model, which is your embedding dimension, the number of heads, and the dimension for each head. All of these are three important dimensions, and you'll have a projection for K, V, and Q. These are weight matrices basically. Okay, guys, please, before coming into this code, make sure that you have watched the transformers video, because I'm not gonna explain the attention computation process. Rather, I'm going to explain the difference between these attention. Okay, the basic multi-head and masked multi-head, all of those are explained already in the transformers video in detail, and I also coded from scratch. The links are in the description, so please check it out. And if you want, the links are also in the playlist 30 days LLM mastery course. Please check it out. Okay, so here we are having the weight matrices with which we multiply the inputs so that it becomes the query key values and then the output projection, and then we have a dropout as well. So what we do in the multi-head attention, first what I'll do is I'll go through these steps, and then I'll explain in stepwise what happens in the code. First, you will project your input queries, keys, and values with those linear layers which we created right now, and we'll reshape the projected tensors to separate across heads. Across heads, compute the scaled output attention, apply the mask if it is provided, so that you prevent attention to a certain position. For example, if it is a causal mask, you shouldn't see the future. If it is padded, you shouldn't see the padded token, those kind of things. And then calculate the attention probabilities, which will provide the attention energy or attention score, which will be multiplying with values to get the attention output. And that attention output of each head is combined together and is projected back to the original dimension. Okay, so that is the flow of multi-head attention. So here if you see, first you are getting the batch size, and you are projecting your input to query keys values here. Okay, and now the shape is batch size, num head, sequence length, head dimension. From batch size, sequence length, and embedding dimension, it became like this. And then now you will compute attention score across each heads. Okay, and once it is done, if the mask is there, we'll apply that mask, and then what we'll do is we'll apply a softmax on this attention score which has the mask filled. Okay, now the shape again remains the same: batch size, num heads, sequence length. Okay, and since now the attention probabilities are calculated, now we'll again do a matrix multiplication on this attention probabilities on the values. Okay, and then we are making sure that those are contiguous, because all of those are random hits. We are combining it together, right? So make sure that those are contiguous once you multiply those, and then we are viewing it to the same original one. Okay, -1 self.d model. Again, what we'll do is we'll project it to the original dimension, where it is now just stacked, but this stack is converted into a meaningful information with this projection. Okay, if you want to visualize the information, here it is. Okay, here we have a function to visualize as well. Python multi-head attention.py cd day. It is day 6. Python. I know we are going slow, but initial days it will be slow because it is a lot more theoretical. But once we move on to a practical section, right, it will be like so fast. And if you want to print the attention values, here you can see, right, the output is there. You can just print the output rather than the shape. I'm just printing the shape because I can see if it is there or not. And here you can see multi-head attention weights for head 1. At head 1, this is how the attention has been. Okay, so closer to purple it is going to be 0, and closer to yellow it is going to be 1. Okay, so this is how the multi-head attention works. Now coming on to the multi-query attention. Here the initialization of D model num heads head dimension is same, but instead of having key projection and value projection differently, here we are just initializing it at same. Okay, so that you'll have a 2 cross D model, and then we'll split it later. Okay, other than that, initialization is same. But here what we'll do is project the input queries across using query projection layer, and then key values using linear layer of KV projection, and then we'll split those. And then we'll reshape the keys and values to align with the number of heads. Okay, because if it is 8, you need to expand it in such a way that 1 is available in all the 8 heads. You will compute your attention score. Everything remains the same after that. Okay, first you'll get the batch size. You are making sure that input is available everywhere. Now when you have the KV, right, you will split it as 2. Okay, and then what you are doing is you are expanding it across heads. Okay, that is what happens. The same thing will be applied everywhere. In every heads it will be available. Okay, that is what happens in here. And now if you see, the shape will be like batch size, num heads, sequence length, head dimension. This is what it has become here, right? After this it is going to be the same code. Okay, not a lot of difference, right? But not this one. If I put multi-query attention.py, even the attention matrix is going to be something like kind of similar, but like there it was more purple, but these are random weights, right? So like I said, all 3 multi-query, multi-head and group query are just differentiated based on the performance side, which means you can't see a lot of difference in the attention maps of each. But when you go for the last 2 types, it will be very interesting. Okay, but with group query, things gets a little bit complicated. Let's go through that. First, you will make sure that the number of heads is divisible by number of groups, because that is when you will be able to split your heads across groups. Okay, and then the normal initializations of D model and heads are there, and then you are also getting the number of groups. First, you need to calculate the number of heads per group. So what you will do is you will calculate the number of heads divided by number of groups, which will say in one group how many heads should be there, and what is the head dimension. You will get it based on the number of heads you calculated. Okay, which is already obtained. Now again we'll have Q projection, KV projection, it is there. What we'll do is we'll have the batch size, which is normal. We are projecting the query across everywhere. Okay, basically across the heads. Right, and then now you have your KV, which is again available at every specific heads available. It is available at every heads, but right now what we are doing is we are splitting it into groups. Okay, now you are splitting it as groups, and in group you will have as heads. Okay, rather than having it at every place, you are having it for groups. After that, if you see the torch multiplication of attention, and then the attention being masked, the dropout being applied to the softmax, and then multiplying it with V and making sure that those are contiguous, and then mapping it to the original dimension and projection it to the original dimension, all remains the same. The only difference is this place. All right, this will make it more computationally efficient. I'm not even going to plot it. You can just do Python GQA and it will provide almost the same plot. But things get interesting with this method, which is sliding window. All right, so what happens in sliding window? First, here you'll have D model number of heads, head dimension, that is same, but you'll have a window size. That is also a parameter. Other than that, the normal projections are there. How the process happens, sliding window is, first you will get the batch size, sequence length, you will project your tensors. Next, you will create a sliding window mask to restrict the attention. This is very important. Okay, and once the mask is there, you will combine it if there is a mask for padding or else causal mask, any mask like that. You will combine it with the window mask, and then you'll apply it on the attention later. Okay, at this step 6. Okay, you'll compute your attention score. You'll apply the window mask, which is combined with the mask, which if it is provided, attention mask, and then the procedure remain the same. Okay, you are getting the query key value, and then what you're doing is we are creating the sliding window mask. So basically what this will do is it will create one for every 1,1. So for example, if it is 3, right, 3 cross 3, it will be 1 everywhere. But here what we are doing is we are creating a trie-U matrix, where what it will do is above the primary diagonal, everything will become 0. Okay, that is what is happening here. We are creating the upper and lower triangular masks, and then we are just and squeezing it to add the batch and head dimensions. Okay, now the fourth step, like I said, if there is a mask already provided, you will combine those together. You can't add it because ones and zeros, right? So you can't add it, you will multiply it. So we are having an AND operation here, and then there is a normal function which is carried on. But if you plot this, right, this will be very interesting to see. Python sliding window attention.py. Here you can see the attention is visible only till a window of tokens, which is here. And what is my window? It is 16. I can only see till 16 tokens. Okay. Really, it is very interesting. Okay, so that is sliding window attention. Now coming on to the last method, which is disentangled attention. Here if you see the initialization, everything is similar here, but other than that we are having a position embedding parameter with a torch tensor being initialized of dimension, max sequence length across head. So at each head, basically it happens, right? So that is why it is initialized like that. And the weights are initialized with Xavier uniform weights. Basically it will be like, -3 to 3. That's all. And then we are also providing the alpha and beta parameters, the learnable parameters, which I said, alpha into relative position embedding plus beta. That is the formula. So we have the learnable parameters as well here. And the function goes like this. First, you will get the batch size projection, and then you'll compute the content-based attention score, which is the normal scale dot product attention. And then what you'll do is you'll compute the position-based attention score by using the relative positions, which is available in this post embed. Okay. And then what we'll do is we'll combine those. Okay. So let's see how that happens. First, QKV is obtained. You're doing your normal, QK transpose by root of D model. That is done. But if you remember, this happens before softmax. Okay, that is how mathematically it was. So first we are getting the relative positions, and for that there is a function already. Okay, here you can see. So what we'll do is the sequence length to which we want, will slice the positional embedding, and then what we'll do is we'll compute the relative positions scores, relative position scores by matrix multiplication, and that will provide you what are the positions we want for this attention. Okay, now this attention, we have it here, right? The position for attention, we'll be multiplying this with alpha parameter and then add it with beta parameter, and in turn this relative position attention is added to content attention, and then the process remains the same. Okay, and if I plot this again, you will find something very interesting. Disentangled attention. Just give me a minute. Yeah, here it is. This is the total attention weights, okay, including content and position. And here if you see, this is the position based attention weights, only for position. Okay, you can see how much this has impacted here. You can see the diagonal, it has become like this. Previously, if you see, in case of the multi-query, everything was just violet to start with. But here, right, you can see a similar pattern of what you can see in here. It has impacted to some extent, right? So that is what you get with disentangled attention. Okay. So yeah, guys, those are the types of attentions which are there in the market right now popularly. So if you have any other methods, you can just let me know in the comments. I'll try to learn about it and I'll make a video if required. So I hope you all like this video. If you all like this video, please hit the like button, share it with your friends. If you haven't subscribed to the channel, please hit the subscribe button, hit the bell icon. I'll see you all in another video. Until then, happy learning.